Welcome back to the deep dive. Today we are really taking a sledgehammer to one of the most vital topics in modern development, Java's memory management system. And we're not talking about, abstract computer science here. We're talking about performance, stability, and avoiding those dreaded crashes.
It's so true. The moment your app starts to scale, understanding the JVM, the Java virtual machine, it just stops being optional. It's essential.
Right.
I mean, Java prides itself on doing the heavy lifting for you, right? Automatic memory management. But if you don't get the architecture, you can write code that fights the system.
And that's just inefficient.
Totally inefficient. So our mission today is to cut through that complexity. We're going to give you the actionable knowledge that we've pulled from the source material.
Okay, so to really get this, let's start with a foundational analogy. Think of the whole Java memory structure, like your brain.
I like that one. It really helps establish the separation of concerns right away.
So you got two main areas. First, there's your short-term working memory. That's the stack. This is where you store the steps you're taking right now, the immediate local things you need to do a task. It's fast. It's temporary.
And then you have the other part, the massive storage unit, the place that holds the actual things you're working with. That's the heap.
The toys.
Exactly, the toys. So if the stack is the instructions, the heap is where you keep the complex data that those instructions are messing with.
And so today, we're going to dive deep into all 5 of the specific memory areas and, maybe most importantly, understand how Java's automatic cleaner, the garbage collector, actually works. Let's start with that fundamental duality then. Stack versus heap. They don't just differ in what they store, but in how they allocate and clean up memory.
Absolutely. The stack is, it's incredibly structured. It uses a last-in, first-out methodology, LIFO.
Right.
So it holds your method calls, the actual execution frame of your program, and all your local primitive variables.
So if I declare something simple like int x inside a method.
Yep. X and its value, they land instantly on the stack.
And the cleanup mechanism here is what makes it so fast, isn't it?
It's instant. When a method finishes, when it returns, doesn't matter if it's a tiny helper function or your main method, the entire stack frame for that call.
Poof.
Poof. It's immediately popped off the stack, memory reclaimed, zero cost to you as the programmer.
So the stack is completely self-managing. It's micromanaging the flow. The heap sounds like it's the opposite, slower, bigger, needs outside help.
Exactly right. The heap is where longevity resides. It stores all your objects. So anytime you use the new keyword,
string, hello, or something like that.
Yeah, or new custom class.
Yeah.
That memory gets allocated on the heap. The local variable pointing to it, the reference, might live for a second on the stack.
But the object itself.
The object itself is on the heap.
Okay, so here's a question. If the stack is so fast at allocation and cleanup, why don't we just store everything there? Why do we even need the heap?
That is a critical question, and it really gets to the design philosophy of the JVM. First off, the stack is thread-specific, and it has a pretty small fixed size.
That's where you get a Stack Overflow.
It's exactly where it comes from. But more importantly, data on the stack is temporary by design. Objects, they often need to exist beyond the life of the method that created them.
Okay.
So if an object is created in, say, method A, but it's needed by method B after method A is done, it has to live on the heap. The heap provides that shared long-term storage space.
So let's walk through an example. If I run the line, string name, new string, Syed, inside my main method,
Okay.
the reference, the variable called name, that goes on the stack.
Yeah.
But the actual data, the string Syed, is stored out on the heap.
You've got it.
So when my main method finishes, the name reference just vanishes from the stack instantly. But Syed is still sitting out there on the heap.
Marooned, exactly. Just sitting there until the garbage collector comes along to deal with it. That distinction is, it's the foundation of all Java performance tuning.
Okay, so we've nailed the 2 big ones. But we said there are 5 specific areas. What are the other 3? The supporting cast.
Right, and we need to give this trio some real attention because they're crucial for how the JVM operates with intelligence.
Let's start with the one that holds the blueprints for everything.
That would be the method area. In modern JVMs, this is mostly managed by a space called metaspace.
Metaspace. Good.
Think of this area as the application's library. It's an archive. It stores all the class metadata, the definition of every single class you've loaded, method definitions, field info, all that stuff.
And there's an important history here, right? For developers who've been around a while, this name has changed, and it wasn't just a simple rename.
That's a vital point. It used to be called the permanent generation, or permgen, and the huge problem with permgen was that it had a fixed size.
Uh-oh.
Yeah, so if you were loading a lot of classes dynamically, like in a big application server or during a lot of deployments, you could just run out of space. You'd hit a permgen out of memory error.
A fixed size for something that needs to grow dynamically.
Mm,
That sounds like a bottleneck waiting to happen.
it was. The shift to Metaspace totally fixed this. It moved all that data out of the managed heap and into native OS memory.
So it can grow.
It can dynamically resize based on what the application actually needs. It basically eliminated those really hard to debug permgen errors, a massive improvement for stability.
That's great context. Okay, next up, the most meticulous component, the tracker. Tell us about the PC register.
The program counter register, or PC register, it's the smallest part of the memory structure, but you could argue it's the most important for concurrency.
Because Java is multi-threaded.
Because Java is multi-threaded, you have multiple tasks running at what seems like the same time, so the JVM needs to know exactly where each thread left off.
It's the bookmark.
It's the per-thread bookmark. That's a
Yeah.
perfect way to put it. The PC register just stores the address of the very next instruction that thread is supposed to execute.
And why is that so critical?
Context switching. When the OS or the JVM scheduler pauses one thread to let another one run, the PC register lets that original thread jump right back to the exact line of code it was on, instantly. Without it, multitasking would be way, way less efficient.
So that's why Java is so good at it. The tracking is literally down to the single instruction.
And that brings us to the last one, the native method stack.
Right. This is for interoperability.
Exactly. Sometimes Java needs to call code that's not Java, high-performance C or C++ libraries, usually through something called the Java Native Interface, or JNI.
But why does that need its own stack? Why can't the normal Java stack just handle those calls?
Because native code, it operates outside the JVM sandbox. It plays by different rules.
I see.
Native calls use different execution frames, different memory schemes. The native method stack keeps that context separate. It isolates the memory frames that the underlying operating system needs, creating a clean boundary between the managed Java world and the unmanaged native code.
So, okay, to sum it up, we've got the stack and heap for data, and then 3 specialized areas for what? Structural integrity, tracking, and external integration.
You got it. And that whole detailed architecture is why the magic of automatic memory management can even work. That automation is what sets Java apart. We don't have to think about malloc and free.
We just rely on the garbage collector, the GC.
We rely on the GC to make sure the heap doesn't just fill up and explode. It finds objects that nobody is using anymore and are unreferenced objects and just clears them out.
But the GC isn't always magical. I've definitely seen it cause performance hits. Given that it has to do all this work, mark, sweep, compact, where does that hit come from?
The hit usually comes from something called a stop the world event.
This sounds dramatic.
It can be. Whenever the GC runs, especially during certain phases, it often has to pause all of your application threads. It needs to freeze everything to make sure it has a consistent view of memory while it's cleaning up.
Okay, let's break down those mechanics. It's a 3-stage process, right? First up is mark.
Mark. This is the identification phase. The GC starts from a set of known live objects called GC roots.
What's a GC root?
Think of active references on the stack, static variables, things like that. The GC starts from these roots, and it follows every single reference path like a spider web. Any object it can reach is marked as live. It's still in use.
So it's basically a big graph traversal problem.
It is, and once that's done, the GC knows exactly what's alive and what's garbage. That brings us to stage 2, sweep.
The cleanup.
The cleanup. This part is simple. The GC just goes through the heap and removes every single object that was not marked as live. They're just deleted.
Okay, so now we have all our live objects, but the memory is probably full of holes where the dead ones were. And that brings us to the last step.
The final critical stage. Compact. Imagine you remove every third book from a bookshelf. You have a lot of free space, but it's all in small, unusable gaps.
Right.
Compacting is the process of sliding all the remaining live objects together down to one end of the heap.
And why is that so important? It sounds like it would take extra time to move all that memory around.
It does, but fragmentation is a silent killer. If your heap is fragmented, you might have, say, 100 megabytes of free space in total, but not a single contiguous block that's even 50 megabytes.
So if your program needs to allocate a big array,
The allocation fails. Even though there was enough total memory, compaction prevents this. It creates large, continuous blocks of free space so that future allocations are fast and successful.
that's a huge insight. So the JVM takes a performance hit now during compaction to guarantee faster performance later. That's a classic systems design trade-off.
It is, and this all leads to the really smart generational approach the JVM uses to minimize these pauses. The heap isn't just one big pile, it's divided into generations.
Based on how old an object is.
Based on an object's expected lifespan, yeah.
Right.
Most new objects start their life in the young generation. And the data shows that the vast majority of objects in Java are short-lived, they're created, used, and then they die very quickly.
So there's a lot of churn in the young generation.
Ton of churn. And because of that, the GC runs very frequently there. These are called minor GCs, and they're super fast because they only have to scan a small localized area.
But what if an object survives? If it sticks around for a while?
If it survives a few of those minor GCs, it gets promoted. It graduates to the old generation.
And that's the stable region.
The stable region, exactly. This is for your long-lived objects. Think connection pools, core application services, big caches. The GC runs much less often here. These are major GCs, and they're the ones that are more time-consuming and can cause those stop-the-world pauses.
So the whole point is to focus the cleanup effort on the area with the most garbage, the young gen, and leave the stable stuff in the old gen alone.
That's the entire strategy. Spend your effort where it's most effective.
And linking back to our earlier discussion, there's a third generation, or, well, the modern version of it.
Yeah. Indeed. The class metadata, now in metaspace, used to be the permanent generation. So it's still that third logical memory space the JVM is managing, holding the blueprints for the code.
So we have this very sophisticated generational system. But we still hear about out-of-memory errors. What's the common reason for that ultimate failure?
The out-of-memory error means the heap is full, and the garbage collector, well, it failed. It ran, maybe desperately, but it couldn't free up enough space. And the most common cause is just poor reference management.
What does that mean exactly?
It means you're holding on to references to objects you don't need anymore. Think of a cache that never expires, or a static list that you just keep adding to forever. Those objects are always reachable from a GC root.
So the GC thinks they're still alive.
Precisely. It's marked as used, so the GC can't delete it. It just sits there, taking up space, until finally the heap is completely exhausted. Understanding that GC lifecycle is really the first step to debugging those errors.
We've really covered a lot of ground today. We've moved way past that simple brain analogy to the core architecture of the JVM.
And to wrap it all up for you, the key takeaways are pretty clear. The stack manages your execution flow and your temporary data, and it cleans itself up instantly.
Right.
The heap provides that long-term storage for all your objects, and it relies on the GC. And that GC process, mark, sweep, and compact, is optimized through those young and old generations to keep the pauses to a minimum.
So we've dissected the 5 memory areas and the complex automation that makes Java run, which should give you the knowledge you need to write code that works with the JVM, not against it.
Which leaves one final thought for you to chew on. Given that the garbage collector runs minor GCs so much more frequently and efficiently in the young generation, what are the real performance benefits of designing your code to use more short-lived temporary objects, especially inside tight loops or utility methods? What happens when you intentionally let your objects die young?